Hey guys, and welcome to the video about linear regression and correlation. Just a little bit about how to watch this video maybe the most effectively. So you can see the slide deck here on the left, and since this is going to be like a decently long video, if you were trying to just get to certain parts, right, whatever I'm highlighting, and you can see the title screens here on the left, right, that's where I'm at. So if you need prediction, obviously go to the end of the video, hypothesis testing, line of best fit, scatter plots, and then up in here is going to be the introduction. So if you need to get to a certain part, fast forward, rewind, and then you can always see the slide deck to my left exactly where I'm at. Okay. But let's get into linear regression and correlation. So for this video, you're going to want to have a TI-84 calculator handy because there's going to be some parts where you want to follow along with me for the calculator instructions. All right, so what is linear regression? So we often want to know how numeric values are related. We want to see, is there a correlation between two things? Like, for instance, the second math exam a student takes and the grade on the final. Are these things related? Is there a correlation? So correlation is another word for relationship. So is there a relationship between two pairs of data? And if so, how strong is it? Right? And two pairs of data we call bivariate data. In reality, though, we use multivariate data. So a lot of different variables going on. We're trying to see how are these things related or if they're related. So linear regression is the simplest form of, is there a relationship here with independent variable x, and we're going to be in two dimensions. So for this, we do need to have a little bit review on linear equations. So think back to y equals mx plus b, right? Y-intercept, b was the y-intercept, m was the slope. We use a little bit different letters here. We use an a and a b instead of an m and a b. But think of it as exactly the same. So x is always your input variable, y is always your output variable, so that's no different. But in this case, b, right, which is the coefficient of the x over here, b is going to be the slope of the line, right? And remember, if you have a negative slope, so if b is a negative number, it means that our slope is trending down, so that's for a negative number, right? And if b is a positive number, that means our slope is trending up, right? And a, which is this guy here, that is an important number because that's the starting point, or what would happen if x is equal to 0, right? If x is equal to 0, right, these guys go away and y is just equal to a. So a is our starting point, b is our slope. Now, for how to get the linear, this is going to turn into what we're going to call the linear regression equation or line of best fit. And our calculator will tell us what a and b is, so that'll be nice. All right, so just a little example here for linear equations. So Aaron's word processing service with word processing, the rate for word processing is $32 an hour plus $31.50 for a one-time charge. So no matter what you do, you're going to pay at least $31.50. The total cost to a customer depends on the hours it takes. We find the equation to express the total cost in terms of numbers of hours to complete the job. So if X is the number of hours it takes to complete the job, Y is the cost to the customer, and $31.50 is a fixed cost, right? So this is going to be our equation here. $32 for every hour, and the hour is the variable, right? Input the hours, multiply it by 32, add the one-time cost to it. That's the cost to the customer, okay? So again, how do we use these? So what's the cost after 2 hours? Plug in 2 for X, add $31.50, you get $91.50. If your budget is only $50, how many hours of word processing could you afford, right? Well, that's an output. So we would set Y equal to 50. We would subtract $31.50 from both sides, divide everything by 32, right? 0.58 hours. So this is just a quick review again of how to use linear equations. We also need this knowledge about these things called scatter plots. So scatter plots are just a way to display the data. So here's a scatter plot here, and here's the 2000, right? X variable, Y variable, right? We plot X comma Y, X comma Y, X comma Y, X comma Y, and then we have a scatter plot, okay? So a scatter plot is just the visual of the bivariate data. That's it. We're just making a plot of it. Here's a couple of different scatter plots that you can see. So this is a positive linear scatter plot, right? Because we're going up, and it looks like we're going up pretty steep. Here is a little bit of deviation over here. This would be a negative, right? Strong negative, right? Because they're all pretty close together going down. This is also kind of negative, right? Because we could see everything's kind of trending down, and it's weak, right? Because these don't form a nice line. This would model exponential growth, and there's no pattern ever. It's a literal scatter plot. It looks like I just threw paint at a wall. I can't determine any kind of relationship here, right? So from scatter plots, you can already kind of see, okay, what kind of relationship is it that we're going to have between our x and our y? And then the next thing we're going to look at is a line of best fit. So line of best fit, right? I can take all this scatter plot data, and what I can do is I can make myself a line that goes through the scatter plot data, and this is always called line of best fit, right? And there is a way to do this by hand, but luckily our calculator is going to create this line for us. And scatter plots can, but not always, will have a line of best fit, right? Like the scatter plot that just had everything everywhere. It's like, well, there's not really a relationship here. Okay. So line of best fit's important because it's how we're going to make from a scatter plot a linear equation that we can then test. We can do predictions with, right? We can do a lot of stuff with. So we start off with a scatter plot, then we create this line of best fit. And how we do that, right? So from our calculator, myself all the way up here. All right, so how do we do this? Okay, so you're given a table of data, right? An X and a Y. On your calculator, put the first column into L1, all right? So go stat, and again, this is for the TI-84. Hit stat, hit edit, right? L1, fill in this. L2, fill in your Y values, all right? So you have an L1 list and an L2 list, okay? After you fill in L1 and L2, so you fill in your bivariate data, you then go to stat, scroll over to test, and you want the linear regression t-test, okay? This is also, again, LINRAGT test. Be careful for linear regression t-int. So that is not what you want. So be careful. We don't want that. Make sure it's linear regression t-test. So once you get to linear regression t-test, so here's what your screen will look like. Your X list is L1, which is why we filled our X column into L1. Your Y list will be L2, which is again why we filled our Y data into L2. Frequency always toggle at 1. Always toggle this to not equals to. And then if you scroll down and hit calculate, this will be your output screen here. So there's a ton of data that it gives us. Okay, here's our linear regression equation, and it's going to tell us so first off, our test statistic is here, because we might need that. Our p-value is here, which we'll need later. The a in the equation is negative 173.51, right? So we would fill this in for the a portion, which you can see I've done right here for the linear regression equation. And it also tells us what b is going to equal to, which I've also filled in for the b value here. So this is the equation. Your calculator gives you what a will be, and your calculator gives you what b will be. It also gives you the correlation coefficient. Again, this will be valuable later to us. Okay, so this is how you get the line of best fit from your TI-84 calculator. And with that, we can do a lot of stuff. All right, we also need to know about this correlation coefficient, this R. So what this R does, okay? So first off, R is always between -1 and +1, always. The size of R indicates the strength of the relationship. Values of R close to -1 or 1 indicate a super strong relationship. If R is equal to 0, there is no relationship, right? So R equal to 0 was that scatter plot where the dots were just everywhere and it just looked like somebody splattered paint on the wall. Okay, that's R equals 0. Okay, R equal to 1 is a super, super strong positive relationship. R equal to -1 is super, super strong and perfect negative correlation. You almost always in real life will never get a +1 or a -1. You could get stuff really close, but this is like a perfect negative relationship, and that's a perfect positive relationship. So positive R means that when X increases, Y increases. So as a visual, a positive strong correlation will look like that. So if R is positive, your scatter plot generally tends up and to the right. A negative value of R means that when X decreases, Y tends to decrease also. So negative correlation. So this is what a negative correlation looks like, right? What can we tie correlation to? You can tie it to slope, right? So you can kind of think of, and don't, it's not exactly, but you can kind of think of R as the slope of your scatter plot of your line of best fit, right? Positive R, think positive correlation, positive slope. Negative R, negative correlation, negative slope, okay? The sign of R will be the sign of the slope, right? As we just saw, that would make sense, okay? And then there's the coefficient of determination. We're not going to use this so much, but it is important to know. So on your screen, right, we also saw the R squared. That's right here. So it's expressed as a percent, and it's the percent of variation in the dependent variable y that can be explained by variation in the independent variable x. So here's our line of best fit, right? Here was our R, here's our R squared. All of this we got from the calculator. Okay, what does R squared mean? Okay, we got that R squared was approximately 44. So approximately 44% of the variation in the final exam grades, that's what our data was. It was final exam grades and third exam grades, can be explained by the variation in the grades on the third exam. Okay, right, that's the thing. 44% of the data can be explained by the variation. Approximately 56, right? Notice these two add to 100. These will always be complements. In the final exam grade cannot be explained by the variation, okay? So R squared, data can be explained by the variation. 1 minus R squared, that's the amount of data that cannot be explained, okay? That's coefficient of determination. The next thing that we need to do with linear regression is hypothesis testing, right? So here comes our alphas, here comes our p-values. Okay, why do we need to use this now for linear regression? The correlation coefficient R, right? It tells us about the strength of the relationship, and it tells us, right, if there is or is not one, right? If R equals 0, there's no relationship here. However, the reliability of the linear model also depends on how many observed data points are in the sample, right? The more data we have, probably more reliable it is. Less data, probably not. We need to look at both the value of correlation and the sample size together to see, like, is this a reliable test that we're doing? We can perform the hypothesis test of the significance of the correlation coefficient to decide whether the linear relationship in the sample data is strong enough to use the model in the relationship in the population. In other words, is the relationship in our sample data good enough to say, hey, I can take this model that I've learned from my sample and apply it to the population, right? Or sample data was no good, I can't use this to model the population. So that's the question here. All right, there's a population correlation coefficient. We call it rho, right? Here, RHO is pronounced rho. So rho is the population coefficient, unknown. R is the sample correlation coefficient. We know it, we get it from our calculator. Okay. This hypothesis test let us decide whether the value of the population coefficient rho is close to 0 or significantly different from 0. And we're going to decide this based on the coefficient of correlation R and the sample size. So let's see how we do this. And let's see in words how this is going to work. So the test concludes that the correlation coefficient is significantly different from 0. We say that the correlation coefficient is significant, okay? So here's the conclusion. There is sufficient evidence to conclude that there is a significant linear relationship between x and y because the correlation coefficient is significantly different from 0, right? That's what we want. what this means is there is a significant linear relationship between X and Y, and we can use this to model the relationship between X and Y in the population. In other words, we have a good sample, this relationship works, it's significant, I can use this now to model and predict stuff about the population. If it's not significantly different from zero, we say it's not significant. So there's insufficient evidence to conclude that there's a significant relationship between X and Y because the correlation coefficient is not significantly different from zero. In other words, I cannot use what I learned in my sample, the line of best fit in my sample, to model stuff about the population. It's no good. I can't use it. It's not a good model. The hypothesis test to figure this out is always going to go as follows. The null is always going to be rho equals zero. The alternative is always going to be rho not equal zero. Okay. The null means the population coefficient is not significant, and the alternative is it is significant. Okay, so now let's learn how to do the test. So we get our bivariate data here. Myself over again. So we have our bivariate data here, and this is there a relationship between the exam score that a student got on the third test and their final exam score, right? The question is there a relationship? It's either close to zero, no relationship, it's close to one, which is strong positive, or it's close to -1, which is a strong negative. Okay, so this is the same example as before. I filled this into L1, I fill X into L1, I fill Y into L2, right? So this guy goes into L1, 1. This list goes into L2, okay? I then do stat tests. I roll over to linear regression t-test. X goes into L1, or sorry, L1 is the X list, L2 is the Y list. Frequency 1, we always set rho not equal to 0. We hit calculate, and we get this output screen here. Now what we're after, right, just what we're after always in hypothesis testing is the p-value, right? So here's our line of best fit. We figured that out, right? Because there's A, there's B, so we got that. Here's our correlation coefficient. And so the question is, can this line be used for a prediction, right? Is our sample data good enough and significant enough that I can use this line of best fit to predict stuff about any student taking any third exam or any final exam, right? Can I use it for that? Null is always rho equals 0. Alternative is always rho not equal to 0. Here's our significance level. Okay, so the p-value is 0.026. We got that from the calculator. It is less than alpha, right? If p is less than alpha, we reject the null. And if we reject the null, then there is sufficient evidence to conclude that there is a significant linear relationship between the third exam score and the final exam score. So because R is significant and the scatter shot shows a linear trend, the regression line can be used to predict final exam scores. So this is what we're after. Can what we found about the sample be used for predictions? That's what we want, right? Did I make a good model to model the population? Yes or no? So we made a good model to model the predictions, so let's make one. So here we go. So same example, we're talking about third exam score and final exam score. So we examined the scatter plot and showed the correlation coefficient is significant. So that's what we just showed in the hypothesis test. We found the equation of the best line, right, which was right here. We pulled that from the calculator. That was the A value, that was the B value. So now let's see how we would use this in a prediction. So suppose we want to estimate the mean final exam score of statistics students who receive 73 on the third exam. The exam scores known as the X values range from 65 to 75. Since 73 is between there, so all you do is you take your prediction, right? Let's say I want to predict what my final exam score would be if I got a 73 on the third exam. Plug in 73 for X, calculate, and we get 179.08. Okay, so we predict the stats students who earn a grade of 73 on the third exam will get a grade of 179.08 on the final exam on average, okay? So that's the power, again, to review, if I take my slides all the way up, right? So you get some bivariate data. You get an X and a Y. You plot it on a scatter plot. you make a line of best fit. Okay. You get the equation for line of best fit. After you get the equation of line of best fit, you do a hypothesis test about your line of best fit. In other words, can I use this line of best fit that I just found to model the population? And you're either going to say yes or no, and that'll be with the rejecting the null or accepting the null. And then if it's good, you can make predictions now and use that line of best fit to model anything about the population and now do predictions with it. And that is the power of linear regression. I hope you guys enjoyed this video. I hope you found it helpful. And if you guys ever have any questions, please don't hesitate to ask.